Hello engineers, this is Mr. Hernandez and I'm here to start the next unit with you guys, which is on simple machines. So you are going to have to take notes on this. There will be an open note quiz and test coming up, so go ahead and get your science notebooks out, turn to the engineering section that you have, and on the top of the page write down Simple Machines, Part 1. And right next to that, write down today's date for whatever date you are taking these notes on. Alright, so let's go ahead and get started here. Now, as we move through these slides, I want you to write down everything that's in the body of the slides. So you don't necessarily need to write down the titles, but you do need to write down what's in the bodies here. And sometimes I'll ask you to write down or draw whatever's in the diagrams here. You don't have to on this page, but sometimes I will ask you to. So let's jump into it. What is a machine? Well, a machine is something that changes forces to make work easier. So let's break that down. A force is a push or a pull on an object. So something that can move an object. And force is going to be measured in pounds, abbreviated as lbs in American units, or in newtons, abbreviated to N in SI units. Now, in science and engineering, we mostly use SI units, so we'll mostly talk about newtons whenever we discuss measurements here. So that is what a force is. Now, if you need more time to write down what's on this page, go ahead and pause the video now. If you're ready, we're going to go ahead and move on. So the other part of that is work. So work is force applied over a distance. And we can calculate work as force multiplied by distance. So if you pull on an object and it moves, you're doing work. So let's take a look at an example of that. Let's say you are pushing on this box, and we can measure how much force you're applying. You're applying 50 newtons of force to push it. And let's say the box starts moving, and you are still applying 50 newtons of force. So the box moves, and you can see it's moving across the page. Now, we want to figure out how much work you just did, but there's something missing. See if you can figure out what's missing from this diagram to calculate how much work we did. If you said distance, you're correct. That's what's missing here. So we need to know how far you moved as well, in this case 10 meters, in order to figure out how much work you did. So here's how we would calculate that. So work is force times distance. And we know that the force is 50 newtons and the distance is 10 meters. So we can plug in what we know. So work is 50 times 10, which means that the work that we did is 500 joules. Now, those are the units of energy in SI units, but you don't have to worry about that too much right now. Now, on this slide, please write down the definition of work, its formula, and I also want you to draw this diagram. Show that this person moved the box 10 meters while applying 50 newtons of force, and also write down this calculation here. Go ahead and pause the video if you need more time for that. If you're ready, we're going to move on. So now we need to talk about mechanical advantage. So mechanical advantage is the amount that a machine changes a force between the input and the output. So you can think of mechanical advantage as how much is this machine helping, and we can actually get a measurement for it. So the input force is the force that you apply to a machine. It's what you are doing to the machine. And the output force is the force that the machine is applying to an object. So think of the machine as kind of standing in between you, and it's taking your input force and turning it into the output force. So let's take a look at how we calculate mechanical advantage. So that is the output force, so the force being put out by the machine, divided by the input force. This is a ratio between what the machine is doing and what you are doing. So if the machine, let's take a look at this. If you put in 1 Newton of force and the machine puts out 2 newtons of force, well, this fraction becomes a whole number, becomes 2. And we would say that that machine has a mechanical advantage of 2. And another way of looking at that is that if the mechanical advantage is 2, the machine is doubling your forces. Now, forces can be hard to measure, so there's another way we can calculate this as well. And that is to look at the distances. So mechanical advantage can also be calculated as input distance divided by output distance. Now, that's because distances are easier to measure. We can do that with just like a ruler or a tape measure, and it's pretty easy to measure and calculate. Now notice here though, the inputs and outputs switch when we look at the distances. They flip over. So that should tell you something about the connection between forces and distances on the input and output. So go ahead and pause if you need time to write down what's on this slide. If you're ready, we're going to go ahead and move on. So this table neatly summarizes what's going on with mechanical advantage. So this first column is looking at what happens to the force that you are applying to the machine. This is what happens to the input force. So let's take a look. So if the machine increases your force, if the machine makes you stronger, then the distance over which that force is applied decreases. So that means that if the machine makes you stronger and you're able to lift something heavier than you normally would be able to, it's going to decrease, it's going to shorten how far it moves. And that means that the mechanical advantage is greater than 1. So if mechanical advantage is above 1, it's making you stronger, but it's not letting the output move as far. On the other hand, if it decreases your force, the distance that it moves is going to increase. And that means that your mechanical advantage is less than 1. And lastly, if it's right in between and it stays the same, if the machine doesn't do anything to make you stronger or weaker, the distance is also going to stay the same, and then the mechanical advantage is exactly 1. So go ahead and copy down this table to your notes just like you see here. If you need more time for that, go ahead and pause the video now. But let's move on. So as the unit says, we're going to look at simple machines. So what is a simple machine? Well, simple machines are a set of 6 machines that have been identified and used by humans since ancient times. Some of these machines were used to build the pyramids, and the pyramids were built, I believe, 5,000 years ago. So that means that these are machines that people have been using for 5,000 years straight. So they consist of the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. And we're going to be taking a look at all of these during this unit. So let's go ahead and start with the lever. So a lever is a beam or a bar that rotates around a fixed point, and that fixed point is called a fulcrum. So here's one example. So on this lever, we can see that there is a bar in the middle. The fulcrum is represented by this triangle here, and it has an input force where somebody is pushing on this, and an output force where the lever is pushing on something else. Now go ahead and pause if you need time to write this down. You don't need to draw this diagram on this slide, but you will on the next ones. So if you are ready, go ahead and move on to the next slide. So the first class of lever has the fulcrum between the input and the output. Now for this slide and the next few slides, I do want you guys to write down the title because that's where I tell you what class of lever we're talking about. So on a first class lever, the fulcrum is between the input and the output. And if the fulcrum is in the very center, exactly in between input and output, the mechanical advantage is 1. So that would look something like this. You can see the input force is exactly the same size and length as the output force. The only thing the lever is doing in this case is changing the direction. So an example of this would be something like a seesaw, where one person is on one side, one person's on the other, and both of them are perfectly in balance with each other. Neither has an advantage. So go ahead and pause the video now if you need time to write this down. And remember, you should write or do your best to draw this diagram as well. And if you are done writing this down, go ahead and unpause, and we can take a look at an example. So like I said, this would be an example of a first class lever with mechanical advantage of 1, because both sides are the same length. All right, let's go ahead and move on to the second type. And again, please write down the title as well as the body here. So on a first class lever, if the fulcrum is closer to the output, the mechanical advantage is greater than 1, which again means you're going to get increased force but decreased distance. So you can see that on this diagram here. So the fulcrum has moved from the center over to the side, closer to the output. And the way that I'm going to show this here is if the force is wider, that is a greater force. That means that it's pushing or pulling harder. And how far it moves, I'm going to use the length of the arrow to show that. So here we can see the output force is much larger, but it's not moving as far. And the input force is has to cover more distance, but it's not as much force. In other words, when you set it up this way, the lever is making you stronger and letting you push harder. Now, go ahead and pause here if you need more time to write down what's on this slide. And once again, please draw the diagram as well. Now, an example of this type of lever with the fulcrum closer to the output is when you're trying to use a hammer to remove a nail. So here, the input is over here on the handle. And you can see it covers a lot of distance to the fulcrum, which is right here where the hammer touches the piece of wood. And then the output force is right here. So the output force doesn't cover much distance at all, but the input force is covering all of this arc right here. And that's what gives you the strength to yank nails out of a piece of wood, where normally you would never be that strong. Now, let's take a look at one more type of lever. So still the first class lever. If you shift the fulcrum from the center to the outside, closer to the input force, this is going to reduce the amount of force that you can apply, but it's going to greatly increase the distance. Now, you may be asking yourself why you would want to increase the distance, but reduce the force. After all, machines are about making it easier to do work. Well, a trade-off of reducing the force is that when you increase the distance, you also increase the speed. And sometimes you care more about how fast something is moving than about how much force you have. So go ahead and pause the video right now if you need more time to write this down and draw the diagram. Then we can look at an example. So trebuchet is an example where the fulcrum is right here, and there is a large amount of weight right here on the input end, and a much smaller amount of weight here on the output end. So when this trebuchet is released, this end is going to move a very short distance. It's just going to go from here down to about here. Meanwhile, the output end is going to swing all the way across, and that's going to make this projectile move very fast so the trebuchet can throw it very far. All right, let's go ahead and move on to second class levers. So in a second class lever, the output is actually in between the fulcrum and the input. So that means the fulcrum is all the way on one end and the output's actually in the middle. Now for these, the mechanical advantage is always going to be greater than 1, which means, again, the input force is going to be smaller but cover more distance, and the output force will be larger but cover less distance. So go ahead and pause here to write everything down, including the diagram. And let's take a look at an example. A wheelbarrow is actually a perfect example of this because the wheel is actually the fulcrum. The output is whatever's in the bucket being carried, and the input is your force on the handles as you're carrying this. So wheelbarrows enable you to carry or to lift much heavier objects than you normally would. That's why gardeners and workers use them to move things like cement and dirt and rocks. All right, so that is the second class lever. Let's go ahead and take a look at the third class lever. So in a third class lever, the input is in between the fulcrum and the output. And for this, the mechanical advantage will always be less than 1. So again, that means that the input force is going to be larger and cover less distance, and the output force will be smaller but cover more distance. And as we looked at with the trebuchet, that means that the output is going to be moving faster. So this is really good for situations where you need to move something quickly, but you don't need a lot of force. And a really good example of that is when you're sweeping. So if you're sweeping, this hand's not going to move very much. That's your fulcrum. This hand is going to be moving a little bit, and that's your input. And then the end of the broom is moving a lot. That is your output. And that lets you cover a lot more ground than if you had a much shorter broom. All right, engineers, so that's going to summarize things for today. So as always, pause here if you need more time to write this down. And make sure that you take really good notes today because you do have a quiz attached to this presentation, and that quiz is actually open note. So you can use your notes while you're taking the quiz. After that, I hope you guys enjoy the lesson. I hope you guys have a great day and look forward to the next lesson starting next week.